Problem 15. When a 4-kilogram object is hung vertically on a certain light spring, let's say we have a spring and an object of 4 kilogram hangs on the spring. Okay. The system obeys Hooke's law. The spring stretches 2.5 centimeter. Okay, here at the final situation, we can say initially the system was at this point. This is the situation of y equals to 0, the equilibrium, okay, situation. When we hung an object of 4 kilogram, we get a elongation. We can say here it's x or y, okay, equals to 2.5 centimeter. When we have a mass here equals to 4 kilogram. Okay. If the 4 kilogram object is removed, we remove this object. How far will the spring stretch if a 1.5 kilogram block is hung on it? So here if we don't have anything, we get a spring like this at this point. It's the equilibrium position of the spring. If we hang an object of 1.5 kilogram, here, we get y prime. Y prime. We have to find the value of y prime. Okay, this is a question. We have how far will the spring stretch? We have to find the elongation of the spring when we have 1.5 kilogram. Y prime equals how much? You know, in general, for the object, here we have the weight, mg, and we have Fs applied by the spring. Here, the weight, we have m1, m prime, g, and here we have Fs prime. And here we have mg and Fs applied by the spring. We have to find y prime. You know, Fs prime equals to k times y prime. You know, k is a constant of the spring. If we use here the same spring here and here, so k will be the same. So we have to find k, first of all, for the spring, okay? You know, to find k, what we have to do, we can, to find k here, let me see, you can use this system because we have m, and we have y. We can write fs equals to k times y. We have y equals to 2.5, and we can find fs as we have here a steady state equilibrium. In this case, mg equals to fs. We can apply Newton's law. So if we calculate fs and we have y, we can calculate k. We come here, we can calculate f prime s by using Newton's law, and we have k, we can calculate easily y prime. Okay? So here, to calculate fs, we apply by applying Newton's second law. What we have, let's say up is a positive direction, okay, or down, as you like, because it will be the same. Here we have fs plus mg equals to 0. We don't have motion because no motion. The final state. Now I take the positive direction as you like, up or down. Let's take up, okay? Up is a positive direction. So fs, we have a plus fs. And here you have to write fs equals to ky. You don't need to write minus ky. When you put plus here or minus, you put the value of this one, absolute value. The same for mg. mg is down, so minus. And here you put the value of mg, absolute value, equals to 0. Okay? So k times y equals to 2.5 minus m equals to 4 in the first case times 9.8 equals to 0. We can calculate k equals to 4 times 9.8 divided by 2.5. We get, don't forget 2.5 in centimeter. You have to put it in meter, minus 2. It's important here, times 10 minus 2. We get 1.57 times 10 power 3 Newton per meter. This is K. Okay, now I can use K in the second case. I take this case. Okay, in this case, also we can apply Newton's law. We have F plus Fs prime up. Here I am using M prime. Fs prime minus M prime G equals to 0. Fs prime equals to K y prime minus M prime equals to 1.5 times 9.8 equals to 0. And K here equals to 1.57 times 10 3 times y prime. Okay, so y prime equals to 1.5 times 9.8 divided by 157 times 10 3. We calculate, the value will be 0.938 centimeter. Okay, this is y prime. Part B, let me write the answer. Part B, how much work must an external agent do to stretch the same spring 5 centimeter from its unstretched position? You know, I have to apply here an external agent. We have to apply F applied on the spring. I push down here to you know, this position is the unstretched position. I have to stretch the spring down to 4 centimeter, okay, by this F. So the spring will be, let's take black. Okay, here we have F applied. And we have 4 centimeter y double prime equal 4 centimeter from this point. Here y equals to 0. We have to find the work done by F. You know, F, we can write. Okay, here we have to use another equation. It's better because, you know, we have the work kinetic energy theorem. Work total on applied on the object equals to delta equals to the work done by Fs equals to minus the work done by F applied. We know this relation in one old video. we calculated the work done by Fs applied by the spring. Here F applied, okay? And Fs must be up in this case. Here we have Fs and here we have Fa. The value of Fs equals minus the value of Fa. And the work done by Fs equals to minus the work done by Fa. And the work done by Fs equals minus K Y. Okay, we can calculate directly. No. We can write here, we want to calculate the work done by Fa equals to minus the work done by Fs, which is equal minus K Y final square over 2 minus K Y initial square over 2. This value here is the work of F spring, and here we have minus. Okay, you know, initially at this point y equal to 0, so this one equals to 0. We get y Fa equals to minus times minus, we have plus, K equals to 1.57 times 10 3 times y final square equals to 4. So we could put 4 times 10 minus 2 square divided by 2. Okay, we can do the calculation. We get omega Fa equals to 1.25 joule. Okay,